So this time I'll be talking about document level models. And the reading was about coreference, as I mentioned, but there's actually lots of different ways you can handle document level models. And I kind of want to map them onto the tasks that we've already handled in NLP and discussed in previous classes. So the first task that we've handled in NLP is language modeling, or that we've handled so far is language modeling, where we want to calculate the probability of a sentence, for example. We've also had syntactic parsing. We have had things like tree-structured models, where we do prediction for things like classification. And we have had entity tagging. So entity tagging, we try to identify the entities in a single sentence. So to do connections to tasks over documents, we can think of document level language modeling. We're predicting the coherence of language on multiple sentence levels. And this is similar to single sentence language modeling, but perhaps more difficult because you need to have an idea of whether things are coherent over the entire document. Document classification, predicting traits of entire documents. And in a way, this can sometimes be easier because you have more text to work from. And entity coreference, which we had the reading about, and also discourse parsing. So how do segments of a document correspond to each other? So this is prediction using documents, whereas I'd say this is a prediction of document structure, and we'll talk about both of these in turn. So first, document level language modeling. We want to predict the probability of words in an entire document. And obviously, one way you could do this is you could do this by taking all of the sentences, predicting all of their probabilities, and multiplying them together. But obviously, the sentences in a document don't exist in a vacuum, and we want to take advantage of this fact. So on the single sentence level, the way we modeled long-term dependencies was with RNNs. It's kind of our standard way of doing it. There are other ways, as we've mentioned before. So a very simple method of doing this is infinitely passing the state. So basically, you take the previous sentence, and you take the RNN, and you just use the sentence that you get from the end of the RNN state when you're predicting the next sentence. So this is super simple. This was done as early as Mikolov et al. 2011. It's also a pretty standard way that people train language models nowadays. So what they do is they cut the document or maybe the entire corpus into kind of fixed size chunks of 100 or 200 words without considering sentence boundaries, and just train one big RNN or whatever to predict. So this is fine. The only problem with this is very quickly you start to run out of memory. And because you start to run out of memory, you have to do things like make your batch sizes smaller, even to the point where you only have a single document in your batch, and this makes training very slow. So an alternative thing, which I talked about before, but I'll just remind you again, is truncated backpropagation through time, which essentially means that you run the RNN on the previous sentence or the previous chunk of words. You get this hidden state here. You save only the hidden state and throw out the previous RNN, and then calculate forwards like this. So what this basically means is your model is still able to reference the information from the previous sentence, but it isn't able to backpropagate all the way into the previous sentence because you've thrown out your computation graph for the previous sentence and you can't use it anymore. So this is an approximation that people make in order to save memory essentially, but it's a suboptimal approximation. You probably would do better if you were able to backprop all the way through. There's other tricky things. If you're interested in them, I can talk more about them. But you can do things like basically saving checkpoints where you throw out intermediate states in the computation graph and then recompute them during the backward pass and stuff like this. But these are more complicated and they aren't used quite as frequently. Okay. So another thing we can do, which I also talked about a little bit in the or no, sorry, this is a little bit different than the thing I talked about last class. But the one way that people have done this before is to try to do a first pass calculation of some sort of document level context and incorporate this as a vector here. So the specific way they did this in the Mikolov and Zweig paper was they used a topic model, which is not a neural network at all. They just ran a latent Dirichlet allocation, which is a common variety of topic model, to get a vector of topics for this document, and then incorporated that into the recurrent neural network as an embedding that they feed in at every time step. So this is super simple. Another thing you could think of doing, which would probably give you pretty similar results, is calculating the word embeddings for every word in the document, summing them together, and using that as input to the language model. So, you know, this would be another thing that you could do super easily. It's not something you backprop into, but it's something that could give you information about the previous thing for pretty cheap. So this would get you things like the topic. So then the question is, what context would you like to incorporate? So as I said, topic modeling. Oh yeah, sorry, actually, this was the, I forgot that I had the reference here. So you could use a bag of words of the previous sentences, optionally with attention over this bag of words. You can also use the last state of the previous sentence. So that's what I mentioned before. The way they did this in this G et al. Paper was a little bit more complicated. They didn't actually just feed the last state as the initial state of the next thing, but rather they fed the last state of the previous sentence to every time step in the next sentence. And the reason why this is good is because essentially if you just feed in the last state, so let's say this is the last state of the previous sentence, like this. When you get to the next sentence, let's say this is the end of sentence number 1. This is the end of sentence number 2. Once you get here, it's already been many, many time steps since you looked at this last. So instead, what they do is they feed in the last state to each of the time steps in the sentence, and this reduces the number of steps that you need from, you know, the like the end of sentence number 2 to the end of sentence number 1 to be linear in the number of sentences as opposed to linear in the number of words in the sentence. So this is another important thing to think about, because the more time steps you have in your neural network, the more likely it is to forget information. So, okay. So these are all kind of old school methods that have been around for a while on things like this. It turns out that actually even just training a big LSTM and passing along the state seems to work somewhat well. It gives you much more information than if you didn't do this, and perplexity goes down quite a bit. But recently there have been some very exciting works using self-attention across sentences. And the very simple idea is that you can just append to the previous sentence, which means that you concatenate the previous sentence tokens with the current sentence tokens and attend to all of them. And what this does, essentially, is this adds context from one immediately previous sentence, right? You just concatenate the two sentences together, and you attend to the previous one. It's almost like a neural MT model or something like that, where you have the previous sentence that you're attending to when you generate the next sentence. But I think the actual really kind of interesting and exciting work here is in a model which was actually done by Zheheng Dai and Zhilun here called Transformer XL. And they have a very clever idea, which is to attend to the vectors from the previous sentence instead of attending to the tokens themselves. And I believe I have a slide. Oh, I don't have a slide, sorry. So let me show the paper and try to explain this. So basically the idea is that they have, in a normal transformer model, or a normal self-attention model over multiple sentences, what you do is you take the previous sentence and the next sentence, and you essentially attend within the sentence. And when you want to predict the next model, you would attend to maybe the past 4 words or something like that. And you would step through with a fixed size context. What they do instead is they have like a fixed segment length, maybe of length 4. And when you have the fixed segment length of length 4, you predict all of the words in the segment, you backprop into all of them, etc. So you learn all the parameters of the model. But in addition to this, you attend to the vectors of the previous sentence. So basically, you're keeping around all of the vectors for the previous sentence. And the good thing here is that when you move on to the next segment that you want to calculate, you're still keeping around the previous vectors. And these previous vectors, in turn, were influenced by the previous vectors in the segment before that. And if you go all the way back to the end of the sentence, essentially each vector, each set of vectors is influenced by all of the previous set of vectors. And then at prediction time, essentially what you can do is you can attend to all of the previous context and step through one by one like this. So in a way, like another way you can think of this model is this is like truncated backpropagation through time for self-attention, where you have this recurrent attention model that attends to the first segment first, then it attends to the second segment and the first segment, then it attends to the third segment and the second segment, the fourth segment and the third segment, etc. But each of the previous segments has been indirectly influenced by all of the other ones. Is this clear? Are there any questions? So when you actually implement this, another good thing about this is there's an efficient implementation, which is basically you create your mini batch, where your mini batch might be words 1 through 40, and then words 500 through 539, and words 800 and 839 or something like this. So you have these length 40 segments of words, and then when you move on to the next mini batch, you just increment each of these. So then you have 41 by 81, 540 by 579, 840 by 879. So you can basically step incrementally through your entire corpus, incrementing by 40 every time. So you only need to maintain the vectors for the immediately previous mini batch. So it's a pretty nice method because it can theoretically incorporate very, very long context, and it can be trained efficiently by just keeping around the vectors from the previous mini batch that you processed. So, the results are also very good. They're much better than other comparable results on some standard benchmarks. And apparently the generation results are good as well. So if you want to take a look at them, oops, this is the anonymous version. If you want to take a look at them, you can ask Zheheng or Jilin to show them to you. So, okay, So this is definitely something I'd recommend taking a look at if you're interested in processing full documents or full dialogues or something like that. Okay. Are there any questions about this? Okay. So then there's a question about how to evaluate document coherence models. So the simple idea of how you can evaluate a model like this is perplexity. And perplexity is, essentially how well do you generate the next words. And if you have a really, really good document level language model, it will probably get better perplexity. It will, incorporate all the stuff that you want to know. And as you could see, the Transformer XL model that I just suggested just did much better with respect to perplexity. However, it is a little bit hard to disentangle the effect of just having a better model overall and having a model that actually is, learning the cross-document, cross-sentence phenomena that you hope it would be learning. So there are other more focused metrics. So one metric that has been used previously for document coherence models is sentence scrambling and unscrambling. So basically you scramble some of the sentences in the document and then try to order them in the proper order. Now I feel like this is almost too easy. This is almost a solved problem. Perhaps people are moving on to more interesting things. Another one was final sentence prediction, where basically you come up with a story and you have two alternative final sentences where it's like Karen was assigned a roommate her first year in college. Her roommate asked her to go to a nearby city for a concert. Karen agreed happily. The show was absolutely exhilarating. Karen became good friends with her roommate, and Karen hated her roommate. So I think the first one is probably the correct one here. But this is an interesting task, but unfortunately the way the data was created with mechanical Turkers, it turns out that even without reading the story, you can do a pretty good job at predicting the right ending. So I think it's an interesting idea, but the execution of how you create the data set is pretty important. Another one is kind of like a closed test where you want to predict final words, etc. And there are things like this. I believe this is called the lambda corpus. I don't know if this is the correct citation for that, but basically they have a document where you need to predict a word, and that word should depend on something that's far previous in the document, and you measure the prediction accuracy according to this. So these are a little bit more focused in trying to figure out whether you can actually reason over long periods. Okay. So moving on to coreference. Coreference was in the reading, so I'll just kind of go through this relatively quickly for the first part and then get into the neural models. So entity coreference, there's other types of coreference as well, but entity coreference is the most common one where you have things like Queen Elizabeth and her, and then you have husband and king, etc. So the first thing you need to do is identify noun phrases mentioning an entity. This is different from named entity recognition because named entity recognition, you actually need to have a name. Whereas for entity coreference, you also have mentions like pronouns or also nominal mentions like a viable monarch. And then you cluster the noun phrases referring to the same underlying word entity. So mention detection is something like this. So a renowned speech therapist and a renowned speech would be different possible mentions, and you need to know which one is the correct one that you should be referring to. So then once you've identified the noun phrases, you can think of coreference as simply a clustering problem given these noun phrases. And detecting the relevant ones is a difficult and important step, but a lot of research kind of ignores this because it's hard and different from clustering. So yeah, so normally this is done as pre-processing. Then components of a coreference model. Like a traditional machine learning model, you need to know the instances that you need to be learning over, and you need to design the features. You need to optimize towards the evaluation metrics, and you need a search algorithm to find the optimal one. So we'll mainly focus on the first three. The instances, coreference is essentially a structured prediction problem where you have an exponential number of possible cluster structures in the number of mentions. So in other words, it's the number of partitions of the noun mentions into clusters. And models are designed to explore this space, and the core difference is the way that each instance is constructed, including mention-based and entity-based ones. So entity-based ones, basically, once you have Hillary Clinton, Clinton, and she, and you've assumed that all of these are clustered together, you're pretty sure that Clinton will not refer to Bill Clinton, while this is more difficult to do if you're just looking at Clinton and Bill Clinton. So mentioned pair models are the simplest one, where we classify the coreference relation between every two mentions, like this. So Queen Elizabeth and her are coreferent, and the other ones are not coreferent. One of the interesting things about coreference is there's actually you can find parallels to things like dependency parsing, which are also ideas of finding relations between two nodes in a graph. So if you think about it this way, this is kind of like graph-based dependency parsing, where you calculate the coherence between two words, a coherence score between the two words, and say the coherence score of Queen Elizabeth and her is high, whereas Queen Elizabeth and husband is low. Queen Elizabeth and King George is low, etc. This is very simple, but it has many drawbacks, like conflicts and transitivity. So you might consider that two are coreferent, but two other pairs of them are not coreferent. There's many negative training instances because most things are not coreferent, and it can't capture entity or cluster features. So entity models, entity mention models, basically you create an instance between a mention and the previous cluster. So this is good, but it does have a couple problems, such as no ranking between the antecedents. And also, cluster level features are non-trivial to design. So how do you design features for an entire cluster of entities that actually summarize the cluster well? And then entity-centric models, basically you create instances between two clusters, making it possible to build up with entity representations. But this also has its problems, like cluster level features are difficult to design, which is a recurring problem. And there's also no direct guidance of the entity creation process in terms of order, et cetera. So in terms of mention ranking models, basically at every time step, you have a choice where you want to rank all of the correct mentions higher than the other ones. And then you always have the new cluster option. So the new cluster option, you will be correct when you have an entity that's not coreferent with any of the previous entities. The entity ranking models, so basically instead of ranking the previous entity mentions, you rank the previous clusters, and you also have a null cluster in case of new mentions. And before neural networks, we had the complex feature design with lots of feature templates. And then there's more feature templates. This is just an overview of kind of the reading that we had and some concrete examples. So then, of course, the important thing is how do we apply, with respect to this class anyway, is how do we apply neural networks to this task? So the advantage of neural network models for coreference is this allows us to learn the features with embeddings. since most of the features that have been used in previous work have been could be captured by surface features that we can look up as embeddings. The other advantage is that it's relatively easy to do things like train towards the metric using reinforcement learning or margin-based methods. So these models can be trained largely end-to-end. Another thing is that actually in the more sophisticated models that have been used recently, they actually jointly perform mention detection and clustering. And you can train all the way from mention detection to clustering in the same encoder model. So this is a really big advantage. This is something that was not easily present in previous models. So the first attempt to do this was essentially, sorry, my slides are broken here. Okay, so basically this is a mention pair model. They tried mention pair models and cluster pair models to capture the similarity between mentions or clusters. And they took all the normal coreference features and used them as embeddings or one-hot features and combined them together. And mention pair features are fed into cluster pair features followed by pooling. So basically the way they created these cluster pair features was by calculating the similarity or these feature combinations between each of the mention pairs in a cluster, and then pooled over these representations. And then this was trained using a structured prediction algorithm called CERN, which is basically a learning to search model that searches through and gets penalized whenever you make mistakes on the predictions. So actually, I think I'm going to go through these ones relatively quickly because there's actually a really nice model kind of at the end here, which is the one that I would more strongly recommend that you use if you're looking at this right away, right now. So then this was followed by deep reinforcement learning for mention ranking coreference models. And basically, it's a continuation of the previous model, with the same features and structure, but they changed the training method or the objective, where this allowed you to choose which previous antecedent is considered, or the choice of the previous antecedent is considered as an action of the agent. And the big advantage that they had here was that instead of optimizing directly towards the ground truth clustering, they rather optimized directly towards the evaluation metric that they used in coreference. So the idea being that the previous method, what it tried to do is it tried to give you the correct assignment of entities according to your reference, whereas this one instead just tried to maximize your accuracy, which is a good thing if your accuracy metric makes sense. So this is also similar to, for example, the sequence-to-sequence models that we trained towards BLUE or whatever else. So in addition to this, because cluster-level features are difficult to capture in the previous methods, this paper by Weisman et al. Did kind of an intuitive but useful thing, which is using RNNs to embed features from multiple mentions into a single representation. So the good thing about this is it took out most of the complexity that we had here, like this kind of like calculate features between all of the mention pairs and do pooling over them, do the cluster pair representation, etc. And just essentially ran an RNN over the mention embeddings to get features, and they were able to actually find that this learns reasonable things without any explicit feature engineering. Okay, So now to the model, a model that I personally found pretty exciting when it first came out. It's the end-to-end neural coreference model. And the nice thing about this is, can we represent all the features in a more typical way with respect to neural networks? So can we simplify the model and more or less remove a lot of the kind of coreference specific feature engineering that was done in the previous models? And the second thing is, can we use the neural network to allow errors to flow end to end, all the way back to mention detection? And mention detection, as I said before, is actually a really non-trivial problem. And if you use a poor mention detector, you will definitely have trouble with this downstream. So this solves another type of error, which is span errors, which were not handled well by previous coreference methods. So the idea is very, very simple. Basically, you run a big LSTM, bidirectional LSTM, to get features for each of the words. And for each mention, you represent the span by a concatenation of the first vector in the span, the last vector in the span, and the sum of all the vectors in the spans. So this is something I think would be useful not just for this particular task, but also other things where you want to represent spans. So sorry, I should mention here, the weighted sum here, this sum is an attentional sum. So they basically do attention over all of the spans here as well, I believe. So given this, you now have a representation for every substring in the sentence up to a certain length. You have to limit the length to 5 or something like this. I forget exactly what they do. But now you have all of these, and this is actually pretty complicated because the number of spans, the number of substrings is actually really, really large, right? And if you calculate, like, let's say spans up to length 10 over a 100-word document, then that's 100 times 10. So you have 1,000 spans. And then you also need to calculate all coreferent pairs, which is all pairs of spans with all pairs of all other spans, right? So that's a million different things that you need to calculate. And that is, that's a pretty big computation to be doing within neural networks, essentially. Even if you're doing simple things like matrix multiplications. So what they do is they have a mention score. And the mention score here is calculated to basically say how likely is this to be a mention. And then based on this mention score, what they can do is they can prune away all of the spans that have really low mention scores. So basically, like, instead of the 1,000 spans that you would have, you prune away and get a smaller number of mentions, maybe 50 or 100 or something like this. And then based on this, you can then take the pairs of span representations and calculate a co-reference score between them. So based on this, they calculate a simple mention ranking model, mention pair ranking model. And so the nice thing about the mention pair ranking model is it's really, really simple, right? It's just ranking whether these two things are co-referent or not. So in the end, the training algorithm becomes quite simple. You calculate the mention score. You prune away the things that have really low mention scores and don't consider them. And then you calculate the antecedent score here. And based on this, you calculate what you think the antecedent of this next word, next mention should be. And they trained this with simple maximum likelihood. It's end-to-end differentiable, except for the pruning part. So I think this is a pretty nice model. Also, I should mention the results are really, really good. The results improve. How do they compute the mention scores? I believe, that's a good question. I actually don't remember the details, but I believe they are calculated end-to-end with respect to the co-reference score. So in other words, you sum the two mention scores and the co-reference score to get your final score here. So what that means essentially is if either of these mention scores are really low, you'll also get a bad co-reference score, which means it hurts your final objective of choosing the correct antecedent. So,
but then you won't be throwing away certain mentions in the first level of training.
You won't get...
we won't be throwing away certain mentions. Like the previous example I stated, we had like about 1 million mentions and we had to do pairwise for all. So if we have mentions, so we'll be pruning them in the first level and then proceed training for the rest of the mention, right? So if mention score is also computed like in an end-to-end fashion, how do we sort of reduce the number of processings?
Oh, you mean at the very beginning of training? That's a good question. I don't remember the details, but they did have a mechanism to do that. But I'd have to go back and read. But thanks, that's a good question. Oh, the question was, if you don't have this trained a priori, how do you prune at the beginning of training to make sure that at the beginning of training it works fine? And the answer is, unfortunately, I don't remember the details, but that's a good question. If somebody figures it out, then I can tell the class about it. Okay. So these are all methods for performing coreference, and another interesting thing is that coreference is actually proven quite useful in some neural models for downstream tasks. This cannot necessarily be said for other types of models. Other types of like linguistic information, but coreference and also discourse parsing, which I'll talk about a little bit later, actually does seem to be pretty useful. So, for example, there are language models that are coreference aware that basically have a coreference step and then use this as a way to pass information from earlier parts of the document into later parts of the document. There's several examples of this, but one example is basically you have I, and you that are co-referent, and us and R are co-referent. So you essentially pass on the information about this by doing attention over the previously mentioned entities. And if you select an entity that has been generated before, you essentially update the representation of that entity in this stack of entities that you have. So the idea being that the representation for I and you will kind of share information from the context that they appeared in. There are also co-reference aware QA models by Buan right here. And basically what they do is beforehand, they run a co-reference system, and then they have a recurrent neural network that basically, in addition to getting the previous state, also just gets the state from the previous co-referent mentioned. So like I mentioned up on the board earlier, one of the really important things for document modeling is reducing the length of the paths between the previous inputs and next input that you want to be predicting. And this is a way to do it in an intelligent kind of entity-centric way, I guess. Okay. So that's all about coreference and uses in downstream neural models. So are there any questions about this? Or can we go? Okay. So now I'll talk about discourse parsing. So discourse parsing, essentially you can think of this as a much higher level of dependency parsing or phrase structure parsing, maybe dependency parsing. Actually, maybe it's more like phrase structure parsing, I guess. So basically, what you're doing is you're taking parts of a sentence. You'll notice this is not a full sentence. You're taking parts of a sentence and combining them together, and also delineating the relationship between these. So specifically, when I say parts of the sentence, there is there's a concept of an elementary discourse unit, where an elementary discourse unit is kind of a small unit within a sentence that has a coherent function in the discourse. These could be things like to thaw ice on occasion, and can dip to minus 213 degrees near the poles, etc. There's a kind of definition of relationships between these elementary discourse units called rhetorical structure theory. And this is, I'm not super familiar with this, but I know the kind of high-level structure. And basically, the high-level structure is that, for example, only the midday sun at tropical latitudes is warm enough to thaw ice on occasion. So this is listed as a purpose. You also have things like elaboration, where the elaboration is giving you more information about the previous thing that you talked about. And these can also be compositional, essentially. So you have a couple elementary discourse units combined into one larger unit. And then, like, you could have a contrast between these two units and these two units. So you build up a tree, and then once you get to the top of the tree, you have the whole document, I guess. Is this clear? Are there any? Okay. So one way that, so like obviously, I guess, or maybe I shouldn't say obviously, but one big problem with this is, in order to perform this parsing task, you need to kind of understand the content of this and the relationship with this, right? And encoding the content of a chunk of words is a highly non-trivial thing. So in order to do that, you basically need to know that these are in kind of a purpose relation, and this is an explanation relation. And you need to train a classifier that's able to do this. So basically, the first model that I know that did this kind of in the neural, or at least distributed representation way, was by using distributed representations to, by projecting features into distributed space for better accuracy. So basically what they did was they took a standard shift-reduce style discourse parser, and they took distributed features over each of the discourse units, and learned feature combinations over them with a feed-forward network. So this is kind of the normal 2014 style way of taking the features that we already had and turning them into distributed representations, learning feature combinations. So then we move on to the 2015 way, which is to learn the features end-to-end. And specifically, what they used here were tree-structured neural networks. And tree-structured neural networks, obviously, this is a task of modeling trees. So using the tree-structured neural networks seems like a pretty reasonable way of doing this. And essentially, the way they did this was they had a binary classifier that said these two discourse units should be merged together. And then based on this, they predicted, yes, they should be merged. Then completely independently, they had a multi-class relation classifier that then said, oh, and this should be in the purpose relation, for example. And they trained this all the way up with maximum likelihood estimation. So of course you can go crazy on this. So You go all the way up to discourse parsing with attention-based hierarchical neural networks. And they had a hierarchical bidirectional LSTM that basically did the composition of the shorter spans or words into larger spans. This is augmented with an attention mechanism because the spans are long and you would want to be picking out the most important words for it. And then they have two bi-LSTMs. One is over the EDU itself to calculate the representation of the EDU. And then they combine the EDU into a representation, into a larger representation. Because this is like a phrase structure parsing model, as I said before, you can then feed this into a CKY-based dynamic programming parser, like the ones I talked about in earlier classes for phrase structure parsing, and find the best result there. Okay. So these are all methods for kind of discourse parsing. I think, I went briefly through the details, but just one of the reasons why is these look very, very similar to the things that we use for regular sentence parsing also. So this is a feature-based, shift-reduce parser similar to Danchi Chen's dependency parsing model. This is a recurrent neural network parser similar to Richard Socher's other models like this. This is a bi-LSTM-based CKY parser, so it's kind of similar to the models, like the neural CRF models like Greg DeRitt's models for phrase structure parsing. So you can see there's lots of parallels between these two tasks, but the details about how you represent the spans, et cetera, are a bit different. Okay. So I actually mentioned this particular example in the adversarial class as well. Not adversarial class on adversarial methods. But just to remind a little bit, unfortunately, this discourse relation classification is a really hard task, and we don't have very much data in the tree banks that we have. So the idea here is to basically take these more difficult implicit discourse classification tasks and train them with explicit discourse classification data. So we have explicit data where we have like never mind because you know the answer. And then you remove the because and you try to make sure that you're also able to predict in the case when you don't have this. Okay. So even if you're not very interested in exactly how you could parse into discourse structure, one thing I should mention is that actually there are some pretty convincing results on using discourse structure in neural models, especially for document classification and other tasks that are kind of important areas. And I feel this is somewhat underexplored. I feel like people haven't, there are papers on this, but people haven't explored it extensively. And a very nice example of this is G and Smith. And basically what they do is they have this dependency structure between here and here. And they train a recursive neural network based on this dependency structure. But more importantly, one interesting thing they find is that essentially this attention term here, this is an attention term over all of the children, is really, really useful. And basically the idea being that discourse structure tells you how sentences relate with each other. And because it tells you how sentences relate with each other, certain things in certain discourse relations are likely to not be very useful for document classification. So if it's just like an elaboration, or it's not, or it's explaining the purpose of something as opposed to explaining the core information in the document, it's pretty easy to figure that out if you have a good discourse parser. And they get very nice results. And more interestingly, discourse parsing accuracy is very important to these results. So they train multiple versions of a discourse parser that have different F1 scores on the RST discourse tree bank. And you can see a very clear correlation with the accuracy on sentiment classification of Yelp reviews with the discourse parser accuracies. So the reason why I really like this result is because I kind of like parsing and I kind of like analysis tasks. And to be able to say, oh, discourse parsing is really bad. It only gets 61% accuracy. But if we extrapolated this 61% accuracy to 90% accuracy, we've solved document-based sentiment classification. That gives you motivation to work on discourse analysis, right? So I kind of like this result here. Okay. So I thought I had more, but actually I guess that's all I have for today. So are there any questions that we have? I guess we'll finish a little bit early, if not. Okay, great. I will finish up there.